Okay, we're looking live now. So I've been slowly moving forward on my automation of Kerbal Space Program, and this step was not supposed to take as long as it did. Anyway, what I'm doing now is I am placing satellites in orbit around Mun, and this is kind of a mix between my satellites that I've put in orbit already around Kerbin. The idea of I have a lead satellite and then I'm going to put up other satellites that are at a phase offset from it. But now it's around Mun. The other half of that is we've been sending tourists in orbit around Mun, and well, the difference between putting a tourist in orbit and putting a satellite in orbit isn't that big. So we start off with the Zero mission, which I've got up here. Go ahead and launch him. It's going to take a while for us to get there. So the guy that's going to be the lead element will go, and he will follow much of the mission plan from the tourist mission to get out there and get into an orbit. His vessel name includes the period of his orbit, which is 0.2, and that's in terms of the rotational period of Mun. So we'll let that go in the background there. I suspect we're not going to get any audio from Kerbal Space Program, but that's all right. In the foreground, you'll see we have some code up. Let me tweak that a little bit, get it where I can point at it. So basically, I've settled on this concept of encoding the parameters for the mission in the name, so I can use the same source code, the same mission scripting to send up a variety of things, much like, well, let's take a look at it on the map. If I zoom out here and turn on the appropriate stuff, this is the constellation of satellites we ended up with. Working our way outwards, these satellites have about a 5 million meter range. 5 million meter? 5 million kilometer? Anyway, 5M. So the first shell is here in kerbosynchronous orbit, and then the second one is orbits with period 2 days, and then periods 4 days. And it gets out far enough that Mun will be within satellite range of this outer ring. Once we get the Mun satellite set up, I will worry about putting other satellites up into an orbit so we form a ring at Mun's orbit. Then we'll start working our way outwards, unless we decide to go ahead and unlock the science for better antennas, which might be a good idea. I'm thinking trying to set up shells like that all the way out to Minmus. Now let's see if we can get enough science out of Mun that we don't need to do it. Anyway, so we're going to put up some satellites around Mun. Let's turn this back down. There we go. Back to the source code here. So having the things like which radius these satellites were on and what their phase offset, having those all encoded in the name means I can do additional launches of additional slightly different missions, changing just the name. And as long as the scripting for the mission is flexible enough, it can do it. So the convention I want, the first set I set up were just C3 phase and the rest of the numbers. So I've inserted in the middle which body they want to be in orbit around. I'm not going to go back and relaunch all my Kerbin stuff, so I don't want to change the way that convention works for them. But moving forward, I'll probably have C03 and then the body and so on. Getting to different bodies out there will take different codes. So likely I won't be using the C03 Go script. There'll be a Mun script and a Minmus script and so on. So current mission is heading up to Mun, and it's got a phase of 0. While I've reserved the rest of these, I decided to just not worry about things like, um, I don't think I'm honoring the altitude. I think well, I'm peeling it off and parsing it here. I'm grabbing H and I and omega and big omega. In reality, my constellation at Mun will simply be circular orbits. So I'll be ignoring H. At well, not zero inclination, at whatever inclination my first vessel gets there. So I'm ignoring I and omegas. So this is very much a subset mission. I will have to do much more complicated code if I want to, say, set up something in a polar Mun orbit, especially a polar eccentric Mun orbit, which might be interesting to do. We'll work that out later. Okay, you saw our antenna just got deployed, and now we have our radio links. I've set this to display the links between my vessel and all other vessels. So we'll see this kind of climb around. It's actually a much more interesting display than the other ones. You can see the green links for the satellites that I have good connections with, and the red links from the ones that I can see, but they're too far. And this is the same plan that we used for our tourists. So change over here. Previously, I just explicitly said, I have this NA, which is the array of parts of the name. I'd say NA sub 2. So what I want to do is extract that out as a service that I can call that'll say, get the next component of the name. So NS gets it as a string, NN gets it as a number. We've got defaults. I do a little jerkery-pokery here to be able to return a default value that's not a scalar. So we can say, get me the number or return a string as the default. So a little weird there. And it encodes all of this stuff. The actual script that gets us to our initial orbit, I repeat most of the comment here. I was looking at a satellite I sent early. I just sent a satellite to go there and get into orbit. And it ended up having a 1.6 million kilometer altitude and a period of 0.44 times the moon's day. I use that to calibrate. So we're going up. We're actually going to be doing a 0.2, but these are the numbers for that first satellite. The mission is very similar to the other ones. We wait for the ascending node, which is going to be a 0 weight here. Countdown, launch, ascent, coast, circularize. We've done all that already. That's already gone by. We planned a transfer to Mun. This is the same one that we've used for tourists, so it transfers to something this side of Mun, so we get this nice far pass by Mun with a periapsis of like 1.5 to 1.6 million meters. Doesn't really matter how high this is, as long as it's nice and high. And then we lightened our ship before he went out, so that all we've got left at this point is the satellite. This means that we can set our attitude. We can rotate the ship as much as we want without using the RCS jets. The weakness of using RCS jets to control your attitude is they also change your orbit. So if you're a long ways away from an SOI entry and you use the RCS jets a little bit, it can really change the way things look. So now we're just going to use our gyroscopes. And we're headed out. I'm going to throw up a console real quick. This is going to list the status of the mission as it comes over. We have a lot of text in front of our graphics here, but that's okay. You can see what's going on with the spaceship here. Whoops. Undo that. Focus on the right guy. Let's go back to the map view so we can see what's going on. So we have transitioned, either we have transitioned or we're about to transition into the Mun's SOI. It's hard to tell on the map view, but I think the presence of this little bit of blue in here is our clue. So starting after we lightened ship, which is before we transitioned out, I've disabled RCS because I want to conserve our monopropellant. Let's throw our fuel up there. So we can see that our monoprop tanks are full right now. We're conserving until we get there. So we're going to use the monoprop to finish off fine-tuning our orbit. Once we're once we're inside the SOI, we're going to circularize. And this will be common to all these guys. The first thing they're going to want to do is circularize so that they are not leaving Moon's SOI. We don't want to risk having the satellite wander out of the SOI because we have no coding to get it back. Once we get in, I'm going to use some adjustment plans. There was a adjust entry point that we had earlier, which allows you the ability to say at a certain time, I want to plan a burn to make my apoapsis and periapsis be these numbers. And there's, please do this at a time. There's, please do this when we go across an altitude. So I can say, do something at a certain altitude, and it will find that altitude and do it. And then I've got specialties for like, make this adjustment at periapsis or at the apoapsis. So our process of setting our orbit here is to, first of all, circularize, as we've done. Then we're going to drop our orbit, drop the other end of the orbit down to the periapsis of our target orbit. And once we get there, we're going to correct at the periapsis to move the orbit around. We're going to jockey back and forth a little bit so we can use maneuver nodes to use the main engine to get us fairly close. Once we're done, we'll do a final tune-up using the main engine, which doesn't get us huge precision. It's not bad, but it's not what we want for a satellite constellation. But this is our last thing we'll do when we do the tune APPE. So we're in the first correction now. All this is still using the main engine. You notice that we still have over 1,000 meters per second of delta V. As normal with my spacecraft, they're kind of over-designed. Okay, so there's our first correction. We have dropped our periapsis down to 884 kilometers altitude over Mun. And once it has, yes, it's happy with it, is now planned a correction down below, which is a 30 meter per second delta V to get the orbit more like what we want. Now, what we want, we actually wanted a circular orbit. So a lot of the complexities of the PE and AP management here become trivialized, but I wanted the code to be general. This does work if we have different AP and PE. It just, we don't want to do that for this constellation. I want this constellation to be circular. So, dragging our apoapsis down into the range of the orbit we want. Tick, tick, tick. Waiting for maneuver nodes is always the longest thing, isn't it? We probably should take a look at these adjust at pieces of code. We could do that later on. The rest of this is going to go fairly quickly here. So now we have a corrected periapsis that we have done. And now we're going to consider correcting at apoapsis. Now it may, so this burn is almost no burn at all. I mean, literally it's a 0.1 second burn for less than 0.0, well, rounds to 0.0 meters per second. So this would just be a little blip on the engine. And this last correction at MD, this says do this correction when we're halfway between periapsis and apoapsis. This is most useful if we've got a eccentric orbit, and it'll do one burn that kind of tunes them both up at once. Now, none of these have exerted any control at all over our angle of periapsis, our argument of periapsis, which means if we very carefully placed our periapsis at a given longitude, this is going to mess it up. So we won't be able to use these for the more specific case. Let's say you're trying to do a Molina orbit, which has a specific longitude that you want it to be rising over, so you want to cover a certain area. we would have to do something slightly different for this. So corrected MD. Again, this is a almost zero burn. That tells me that we're very close to circular here. And if I look up at this display, which may not be readable, Kerbal engineer is telling us that we're within a few 100 meters of absolute circular. So that correction happened. So this tells us that we had a facing error of 3 degrees. So our forward vector was 3 degrees off vertical. We fixed that. We had a roll error of 1.3 degrees. We fixed that. And now we're flashing up. We had a period error of like 4 seconds. And we did a little puff on our RCS. I didn't get a chance to show you that. I will see if I can be focused on the ship when we start putting our other satellites in. And now it's just going to hold the attitude and the period. So we have a period that is very, very close to what we're supposed to have. You'll notice our links here. We have a dim green link back to this ring of satellites. So we do have connectivity. When we get our satellites in orbit here, there'll be at least one satellite over on an arc that's nearer to that ring. So we'll have better connectivity there. So let's go start our second one. So back to the Space Center. I think I'm going to use, hey, let's do 5 satellites in Mun Orbit. This is going to be a follower. So we need to bring up the next script here. And change the name. You may have noticed when we started that there was the saved name in here was 288, which is our last one in that same constellation, because I did a test run of some of these just to make sure that they could get into orbit. So now we are launching. All I've done is change the name. I hit the launch button. And when we start in on our scripting, we have all the same conventions, but in reality, we're going to ignore most of that. We pull off our phase out of one of the components. So this hasn't been adjusted yet to do the parsing of the name properly. I'm just grabbing sub 3. I'm setting it to 0 and reconstructing the name of the lead vessel. And it might have even printed it. Let's see here. I didn't print the name of the lead vessel, but it would have been C03 Mun 0000.2. So initially, I want to collect the ship and the body. So the body is going to be Mun, and the ship is going to be the lead element. So I collect those, I clear the target, and I tell the targ system to reload whatever is persisted. This way, if we reboot, we can reclaim these objects and then set our target to whatever it was set to, because during our flight, our target will be the Mun until we get into Mun orbit, and then we need to target our lead element to get into formation. I still have a script here for awaiting engineer's input. During development of this, I would scatter in executions of await engineer, which would basically wait until I toggled the gear before it continued. Now that's going to go away. Let's get rid of that now. So similar mission plan all the way out until we get into Mun orbit. Once we get to Mun orbit, our job has changed. With the first vessel, our job was just get into a circular orbit at a pre-computed, pre-specified altitude. For this vessel, what we want to do is switch our target to the target vessel. So we locate our lead that we're going to get in formation with, and then ignoring anything else that's configured about us, we find out where the lead is, and we want to get into its same orbit at a certain phase angle in front of it. So you'll notice that we are ignoring all the configuration parameters. The only thing those are used for is they're part of the name that allows us to look up our lead element. So same thing as all of the other satellites that are following. We match the plane of our lead element. So we're in a circular orbit around Mun at some distance. So we do a plane match, and then we transfer into its orbit. This uses a Lambert solution to get us from where we are into its orbit at the appropriate phase offset. That's how Plan X-FIR has grown. It's evolved into doing all of that for us. It'll plan that for us. I'm going to continue going through the code that's going to happen when we get to Mun. We're no longer, we're nowhere near Mun yet. We're still launching, for goodness sake. So we plan the transfer, and then we have this little loop where we execute the maneuver node. We make sure that we're lightened. So the first time we do the transfer burn, we will be using our ascent engines. Once we've lightened, we have left just our satellite. And then it plans out a correction. And if we're good enough, it's going to skip right on down through. But if we're not good enough, Plan Core will say, oh, I need to do a correction burn, and it will leave a maneuver node for us. We go back and we execute it. And we will continue to execute maneuver nodes until we are arriving good enough. Now, for this particular mission, so this bit of it, this will actually get us into the exact same orbit as our lead element, plus or minus whatever error I can handle. The big engines that we're using for this, they're actually very small engines, but they're big relative to what we want. Have a bit of slop in them. So for some reason, I have decided in the end that I want to do a circularization at the end. What I should be doing is execute the final node. There's a better way to do shift to executing the B2 burn from the last Lambert solution. So we actually had a burn from Lambert that told us when you get there, do this correction. So I'm going to put a question mark on that. If we did not execute our B1 burn from Lambert precisely, then the B2 burn is going to be different. But what we really want to think about is what burn do we want to execute to match the velocity at our destination that puts us in the appropriate orbit. And instead, what I've got here is when I get to my periapsis, I'm going to circularize. This absolutely has several assumptions. The first one is I am descending into the matching orbit. And the second one is my matching orbit is circular. So once we get there and we get into the right orbit, we're going to circularize. Now, Plan Core just gets us aimed at the destination. This also assumes that the periapsis of our transfer orbit is on the destination. Oh, we just happen to have been watching watching Kerbin during this process. So as we got there, you notice our periapsis, we have a free return trajectory. Small changes in our vessel moved our final periapsis above Kerbin up and down. And that last little bobble you saw was what was changing just because we were changing our attitude, because well, it's gone now, but we actually had our next stage on there. So we were swinging a baseball bat around, and it was changing our orbit because we were using our CS to do that. This correction was computed after we got rid of the other stage, and we're doing the whole thing using our reaction wheels to point us. So this time when we do our correction, we should actually come out with our orbit much better than it was. My goodness. My co-pilot is being chatty. Hey, meow. Oh, she's just saying hi. So the burn went by, and now we have this nice intercept with Mun, and we will fly by it, and we will return on this free return trajectory, except, of course, that our mission plan says, once we get there, we're going to do all this logic. So let's watch as it happens. We've already walked through it verbally. So you can already see that we have a radio link to one of our satellites around Mun, the first one that went up. He's our lead element, by the way. So now we are just waiting on our transfer into the Mun SOI. So I'm going to zoom in just far enough that my radio lines fade. You can still see them there, but they're not going to dominate. So we've arrived in the Mun SOI. I'm going to pause briefly and then schedule a circularization here at our periapsis. So this is at a radius of about 1.5 million kilometers, which is way higher than our other relay satellite. Let's turn the relay. I have relays turned off on the map because there's 38 of them now. So there's our orbits of all of our relays. But here's our lead element and the orbit we're going to be in. Don't need to see him really. So our circularization at Mun is costing us about 180 meters per second. This is pretty consistent. I remembered circularizing far above Mun as being about 150 to 200 meters per second from many, many years ago, and 180 feels about right. I must have been doing similar trajectories to Mun. So we get ourselves circularized here. At this point, we're going to switch targets. Because now we need to figure out where we're going. So this says set target to, and there's our lead element, 0 phase, 0.2 period, and we're at 72 degrees ahead of it. So a little bit of Lambert planning went by, and now you see that we have a trajectory. When we get there, that will take us downward to our destination orbit. So the difference between these, I chose 0.2 Mun days as our period here because I'm at about 0.4 to 0.45 here, and I figured that I didn't want to have it, too close, or we would, be spinning around and around and around and around in a higher orbit trying to get into a lower one. If there's a bigger difference, it means you don't have to wait as long to catch up with your solution. Okay, so we have executed our initial burn, and we are now transitioning down to our target orbit. Notice that the plane change went by pretty much without any action. There's a plan go here. Okay, so if we didn't do any plane change, it meant that the plane was already good enough, and that's quite likely. So focusing in. Get down to here, and now we are circularizing. So apparently there was no correction actually needed. So the first burn we did got us so close to our goal that we didn't need to do a main engine correction to get ourselves to the right point for the next part of the mission. So now we're going to circularize. And again, this is where I think that we should, instead of circularizing, we should be burning to attain whatever velocity we should have to be in the same orbit as our lead element. That's probably predict their velocity at the appropriate time, at the appropriate phase, and then correct to have that velocity horizontal where we are, because we're probably not exactly at the right phase, and we're probably not exactly at the right inclination, so we're going to want to map it. But if our scalar speed is correct, Yeah. So the important thing will be to match the scalar speed and match the radial velocity so that we get our apoapsis and periapsis in roughly the right place. And then something very close to that, tune that direction very precisely to match the correct speed so that our orbital period is correct, because our major priority here is having the absolutely perfect orbital period. So you notice there's corrections here that were, there was a facing error of 3 degrees, means we were not pointed directly up and we needed to roll by 10 degrees. So these basically were correcting our attitude to get us into the perfect attitude. And again, I did not have it focused when it did that, but we would have seen some puffs on the RCS to fine tune our period to match. Let's go grab the next one. So that was 72 degrees phase. The next one's going to be 144 degree phase. Get that launching. And while this mission is continuing pretty much without any kind of intervention, let's take a look at some of the code that was involved here that we kind of glossed over. So during the launch, I had these plan adjustment at things. Let's take a look at that real quick. My coding style is highly tuned so that code folding under VS Code is efficient. So you'll notice here that we've got plan, and this is all just one line. If I put the close brace on its own line like I normally would do, there would be extra lines in here, and I only get half as much on the screen. So adjust at. The main adjust at entry point basically takes 3 altitudes. It says when you get to the first altitude, adjust your orbit so that its periapsis and apoapsis are the other 2 altitudes. And that's the most general version. Then we have adjust at MD, which says when we are halfway between our periapsis and our apoapsis, burn to adjust so that periapsis and apoapsis are H1 and H2. And they all depend on the same, I better mention this first. The way we do this is we iteratively find the time at which we are next at that altitude and adjust. We then pass control over to something that says at this universal time, figure out what we need to burn to get into the orbit with that periapsis and apoapsis. Then based on that, we've got adjust at periapsis and adjust at apoapsis, which are just as simple as they sound. We're going to do the same adjust at UT using our built-in ETAs for periapsis and apoapsis. Then the hard part of the logic basically says, figure out where we are at that time. Okay, so ship from body and ship VREL body is our body relative position and velocity, so that we can figure out, okay, what's our current, we know what the orbit needs to be shaped like. What orbit are we in right now? How fast are we moving at that instant? And how fast should we be moving? There's special cases here. If we are, we've got some cases here. If we are between the desired periapsis and the desired apoapsis, then we have to decide whether we're going to be ascending or descending. If we are below the periapsis or above the apoapsis, then it's simple. And so look at the simple case first. So we're below the periapsis or above the apoapsis. We're just going to want to have our velocity be horizontal, because that's going to get us as close as we can to having the correct periapsis and apoapsis. And if we aren't, then we need to decide what is our desired vertical speed. And the math is right there in front of you. So we already know things like our lateral direction. So desired speed prograde, we use vis viva. Given our current radius, our radius of periapsis and apoapsis, that will give us back what our speed should be at our radius. That's speed in the prograde direction specifically. Then we have, what's our speed at our periapsis of that orbit? So we're going to figure out what our lateral speed is using Kepler's second law. So we can find out what is our velocity at periapsis. We know that's a lateral velocity. We take that lateral velocity at periapsis, multiply it by the radius at periapsis and divide it by our radius, and that gets us our desired lateral speed. That's because the product of your lateral speed and your radius is constant across your orbit. That's Kepler's second law. You sweep out equal areas in equal times. So your area sweep rate is proportional to your speed, your lateral speed, not your prograde speed, your lateral speed, and your radius. We have a condition here that says take the vector from the ship to the body, multiply it by ship from body, so vector from body to ship, dot product with the vector velocity. So this says, what is our radial velocity going to be? All we care about is the sign here. We could normalize these and all that. We just say if it's negative, if the dot product of those two is negative, that means that we are in fact headed inward. If we're headed inward, then we want to end up with a negative radial speed. So there are two solutions to this. We can be headed inward or outward. Matching our current radial velocity in sign is the one that's going to take less energy. So now our desired velocity is going to be the lateral direction vector times the lateral speed plus the radial direction vector, which is ship from body normalized, times the radial speed. And you can see that the other one with the zero radial velocity is just take this stuff up here and then say, well, our radial speed is going to be zero. So then you eliminate the dead code. Work out our dv, which is desired velocity minus the velocity that we will have at that instant. And we do the planning. We skip printing it out this time, and we're all done. That will leave us with a node that will make that correction. There's one further step I could do, which is to look at the node and say, well, not even the node, look at dv before we build the node and say, if there's no significant correction, then skip making the node. Because all of my code that executes nodes can do things like, well, if there's no node to execute, just we're done. So we could have this not produce a node. As it is, if we are exactly on the right orbit already, this is going to build a node that has a zero. The rest of these are unchanged from previous versions, although I notice that approach AP is got an extra carriage return in there. There we go. So fold it all up and look at it here. And there's our table of contents back again. So in the background, we are coasting to Mun. And I'm going to watch the rest of this in this view. Let's turn off the code editor for the moment. Now, I believe at the moment we transition from one SOI to the other, we get an immediate reorientation of the spacecraft, I think. I could be wrong. Yep, we do. There we go. There's different notions in my code in different places about what our neutral pose is. And early on, when I was doing a lot of send a Kerbal up to do some EVAs, I set up my pose, my neutral pose, so that where the Kerbal got out was always looking down through the spacecraft at the body. But for the ComSats, I'm setting up their neutral pose to be zero, to be constant relative to the star field. This way, when we switch to them, in theory, we shouldn't have a burst of activity on the spacecraft to roll it. You know, it was facing Mun before, and now it needs to roll by 90 degrees to face Mun again. All I want to do is lock its orientation to the stars, so as I switch from satellite to satellite, they don't reorient. This will save us, fuel if RCS is turned on. If RCS is turned off, it means we won't be eating into our batteries. As it turns out, these satellites have plenty of both. They still, I haven't even touched the monoprop yet. We'll be touching that later, just a little bit. The monoprop is the only thing we'll be using for maintaining our station once we get there. So little bursts of monoprop to adjust our period as needed. Later on, we'll be doing things to instead of getting exactly the right period, adjust our desired period by how far we are away from our assigned position. So we'll start to think about assigning a position. Not there yet, but that's one of the reasons why I over-designed this in terms of fuel. So, so we're not in the idle pose because we are posed to execute the next maneuver, which is this. We are transferring. You could do it. Oh, 20 seconds, yeah. So in theory, if I'm not, in the last few seconds before this spacecraft has to do anything, I can switch spacecraft and come back to this, and the code picks up at the same flight phase. So it'd pick back up and say, oh, what was I doing? Oh, yes, I was, about to do circularization. So these are all this code is proof against getting rebooted as long as you're not rebooting in the middle of a burn. You might miss the time to stop the burn and burn too much, or you might miss the time to start the burn and not start it in time. But yeah, if you're just, transiting out somewhere, you're fine. So going behind Mun from the sun, you notice our electric charge crept down, but it filled back up very quickly. We are again pointing in the proper direction to do our circularization. Oh, excuse me, our apoapsis correction. Those maneuvers around Mun at this altitude don't take a lot of delta V. It's one of the reasons why we use RCS to do our corrections, because a very tiny amount of delta V coming out of that big engine has a very large effect on our actual orbit. So we have to use something that's very tiny. Okay. So we are in a roughly circular orbit at 885 kilometers. Now we have explicitly asked for a circularization. Again, this is the phase that I want to replace with burn to get in the proper velocity for the possibly eccentric, possibly inclined orbit that we wanted. There's a bunch of work that has to happen if we're going to be selecting an inclination and a argument of periapsis and a longitude of the ascending node. A lot of work before that'll work. But for the constellation that we're putting up right now, these nice circular orbits with constant phase offsets work just fine. So the recircularization, very, very small burn, as it was over that quick. And we pose. And now we're going to drop into our station keeping code. So fix the facing error and fixing a roll error, and then a period error of 0.857 seconds. And that's how much RCS firing it takes. Oh, 9 seconds. Okay, so I'm not sure what happened there. I'm really not sure what happened there. I think there is some weirdness in how the period is computed. I've seen this happen before where I'll burn to correct my period and it'll start by going the wrong way. And this should not be a non-minimum phase system. Anyway, so we are now in the proper orbit. Notice that the orbital period, if I look at my MechJeb displays on the left, those may be too small to see in the recording. My orbital period is 1 day, 1 hour, 43 minutes, 17.14 seconds. And my target orbit is 1 day, 1 hour, 43 minutes, and 17 seconds. It doesn't print decimals after that. So I am very close to the correct orbit. My phase angle is 216 degrees. This is 144 is my phase offset. Those should add to 360. Let's see here. 350, 10. So 300, yeah. So the phase angle and the assigned phase angle are adding up to 360, so that's correct. I probably should have reversed that. So yeah, this is really the, if we were the leader and we looked at 144, we would see a phase angle of 144. Let's double check that. Why not? So we can see that our orbits are not exactly the same here. They are all roughly circular. They are not inclined the same, although no, they're pretty much the same. So somebody is not circular. Let's go take a look at the leader. So I'm going to switch to the leader real quick. So part of the station keeping is that I'm only trying to correct. Okay, he had a roll error of 145 degrees. So I'm wondering if I'm using the wrong coordinate system, and I'm actually using a coordinate system that is relative to Mun from this location. So if my period is correct, I'm not doing anything to make it more circular, because if I did that, we would be spending all of our time correcting our eccentricity, which is a little more expensive, and eating into our monoprop. Even though we haven't used hardly any monoprop, different missions are going to come up with different amounts of monoprop that they've used. So let's take a look at this guy. So the 72-degree guy. Oh, I was going to take a look at what we displayed for the phase angle. Oh, well. Yeah, my posing for this direction for my attitude here, this is not right. Pop this up real quick. Take a look at it. So, what I'm doing to set my steering is I'm saying steering to lifter up of 2 absolute vectors. I assumed these were using a coordinate system that was not rotating relative to the stars. Apparently, the coordinate system I am in is rotating, excuse me, it's rotating along with something. So it's maintaining an orientation which is rotating. I don't know whether it is zeroed relative to facing Mun or zeroed relative to the orientation of my launch site on Kerbin, but it's not zeroed relative to the sun, relative to the stars. So I will have to go in and think about that. There is a master vector which points out along a master horizontal direction, much like the y direction is constant in Kerbal Space Program. There is a vector in the XZ plane that is held constant. I may have to rework my code to use that vector for my up vector instead of V100. Anyway, go back to here. I'm in 72. If I target 144, then this says that my phase angle is 71.62. So it's about 72 degrees. It's close. Since we're not actively trying to maintain that at 72 degrees, that will drift slowly over time. If I switch to the leader, but I think, let's turn off this. There we go. If I switch to the leader, so I've focused on the lead. If I set target the 72 degree element, then it has a phase angle of 72.3. So it's a little farther from me than it should be. And the 144 element is a 143.92, so it's a little bit closer. But we're doing 5 of them, which means that we will still end up with a nice, strong set. Let's do the 4th one. And while this 4th one is launching, I will see if there's anything at all intelligent I can say about another bit of code while this is getting up into orbit. That's 144 plus 72. We moved back and forth a few times, so I need to load up the vessel again. So this is going to be 216. So 72 for each one. So while that is launching, let's see, what can we say about this code? Other than, I don't think the loop here is needed. I think we can just do a single correction and be done with it. Other than we are not implementing eccentric or inclined orbits at all in any of this. The follower code will be just fine. The follower code will latch on to the leader and initially match it. And then, of course, it does that circularization, which is going to destroy the eccentricity. What did I change? I'm going to bring up my logs real quick. I don't have things set up to throw this up on the screen. Let's see. Looking for significant changes. I think that the change to the plan to do the just at, breaking all those out into various things, I think that was the only, that's the only real change. Let's see, sweep up, sweep up, sweep up. I had to change to control. That's just a threshold change. Lots of removing a lot of debugs. My maneuver step, maneuver step. Not really that important, but small tweak, which could be interesting. So just to review, I want to repeat as I often should, that the maneuver code I got here came initially from Kevin. Cheers, Kevin. He YouTube's under, and he did a series of bits of code for creating and executing maneuver nodes, and I ended up basically ripping into it, tearing it apart, and putting it back together. His maneuver execution code, you call it, and it doesn't return until it's done. And I wanted to have a framework where I called a piece of code that ran very quickly to completion and return. So I needed to invert the control. So rather than having code that waited until a certain time, I would put code in that says, if we're not at that time yet, then return, and arrange to continue onward. So almost a coroutine change. And that has grown. So maneuver step is, I really need to refactor this for simplicity. Let's put it that way. So abort and lack of a node and time warp at the top, all handled. Terminations, conditions, handled. What we changed was there's certain bits of information we want to set before we start the burn and remember during the burn. And I had a heuristic I was using where if we weren't at the burn yet, I would update something. But I was still, every time through, I was recalculating the start of the burn time, which meant that the start of the burn time could move into the future, confusing logic. So now we have a much more explicit, are we in the pre-roll? So we have something called a pre-roll period, where if we haven't gotten to turning on our engines to do the maneuver, pre-roll is going to be true. And while we are in pre-roll, every time through during pre-roll, I am going to recompute our burn time and our wait time, and I'm going to set these bits of retained state. And if we reboot during a burn, this is going to re-execute the first time through. Forgive me. Our trap out here is that if we go more than 10 seconds between calls, 10 in-game seconds, we're going to assume we're back in a pre-roll again, because we may stop calling this method during a burn. And we don't want to have it assume we're in the same burn later. So when we transition out of pre-roll, we stop recomputing these. So we'll have an initial burn and a start time and a final time that we committed to the moment we started burning. So having done that calculation, I then compute wait time. The computed wait time is the committed start time minus the current time. Well, once we have gone out of pre-roll, wait time is never going to be reset or anything. That's fine. So once wait time goes negative, once our time exceeds the maneuver start time, then we set pre-roll to false, saying we're done with pre-roll. Whether we're in pre-roll or not, we're going to establish a function delegate, a delegate to an unnamed function, that's going to compute our desired delta V, which is going to be, similar to the burn in some ways. We're going to tweak it. We've got a couple conditions where we're done. So if we don't have a node, we're done. If we have a node and it's not the same node, we're done. Then we look at the current node's burn vector and we say, well, if the burn vector in the node, if you are burning in KSP while you're, at some point in this code, if you're doing a burn, the delta V, the burn vector that's in the maneuver node, gets adjusted on you. So it will keep track of what's left to do in this burn. Well, if it swings around to where there's no component of it that's forward in its old direction, so if it swings around by more than 90 degrees, we're done. Okay, that's pretty much Kevin's original condition, which keeps you from chasing it as it wanders all over the nav ball. And for a while, I was doing that, and I've gone back to using this dot product. So So if our burn vector, if we manage to go as much forward as we're supposed to do, and we overshoot by a little bit, that vector is going to whip around behind us. We don't want to turn the ship 180 degrees and burst our engines. We're done. We also have a deadman timer. So I compute a final time. If we get to that final time, even if we haven't done anything, we're done. So if you get to final time, if you haven't managed to meet your burn by then, cancel it. And that final time is going to be the start time plus the computed burn time plus another minute. So we're going to give ourselves an extra 60 seconds after when we think a burn should end to do any tail offs. That's because we do have a gradual tail off in our burn. And sometimes you will stage, and the engines you're staging into are lower or thrust. And yeah, there are still situations that can fool this because my maneuver time computations don't take into account staging. So plus 60 seconds is more than long enough. I have seen us take an extra 30 seconds after a planned end of burn to finish it up. So that's why this is 60. Anyway, if we get to that final time, we're taking too long, we're done. If we're not at the start time yet, we're not done. We don't want to return a 0, but we want to return a burn vector that is very, very tiny, but in the correct direction. This way, before the burn, we will slew around and point our nose in the correct direction, but we won't light the engines. So this is a vector in the correct direction whose magnitude is 1 over 10,000. If we don't have any available thrust, well, we're going to calculate how much thrust. So the value we're returning is actually a thrust value. It's a vector in the direction we want to burn, whose length is our throttle setting. Well, if we have no available thrust, then computing our throttle setting would overflow. So we say, well, if we don't have any available thrust, then use this same thing. So a vector in the correct direction with tiny, tiny length. So if we get past all that, it means we do want to burn. We do want to burn in a certain direction, and we have significant thrust. So we calculate the burn vector magnitude times the ship mass divided by the available thrust. This converts it from a change in velocity to a force in kilonewtons. And we say, well, okay, TT is a bad name here. I'm not sure why this is called TT. Oh, right. Okay, never mind. Rewind. BV mag is the amount of delta V we want. If we assume that we are burning at full thrust, then our delta V will cancel this burn vector. This is how long it will take for us to cancel that burn vector with all available thrust. So delta V times mass divided by force gives time. Then we say, well, if this would take less than a very small amount of time, good enough being, what did I say good enough to? 1,000th of a second. So if the amount of the burn remaining is less than 1,000th of a second at full thrust, or 1/10 of a second at 1% thrust, then we return 0. Remember, this 0 vector is recognized through the rest of the system as we're done. Otherwise, we've got a decent amount of burn to do. It's going to take us a significant time, so we go ahead and return this BV value, which is a appropriate burn direction and throttle setting. Throttle setting? No, this is an appropriate burn direction and requested change in velocity. So set that up. Then I'm going to call it once manually and look at it and say, well, if this returns a 0 to me right now, then we're already done. And this step is going to get called periodically. So every time we go through here, we're going to check and say, well, would it return 0? We still need the entire function for later, but check it right now, see if it would return 0. If it would, then clear out final time and use tell control DV we're done. This sets up the old pose. This is the pose where we're facing the body. Let's switch to watching the spacecraft here real quick. So that's our second I'm done check after the initial ones. If we get down below that, it means that our DV function delegate is telling us we need to burn. So then we call up the CTRL module and say, please control the throttle and the steering to give us a delta V controlled by this function, which will return our remaining delta V every time you call it. And 115 are some parameters for DV that should have gone into before. Basically, this controls how you are adjusting that throttle based on your angle error. And I think one of those is a gain. Anyway, I'd have to look at the code, not important. But this establishes my layer called CTRL, which talks to the cooked layer in KOS to get me this change in velocity. Now, get that set up, even do that way in advance. And we say, well, if we've got more than 60 seconds left to wait, then we do this. Oh, if our steering vector and our facing vector are nearly the same, we're pointed in the right direction, then we can go ahead and think about warping. So check to make sure we're pointing in the right direction. Make sure our warp mode is set to rails and not physics, so we get a decent one. And then we warp to 30 seconds before the time of the burn. If that's not true, then we're going to wait one because Control DV is working on getting us our attitude set appropriately. Okay, and here we are working on our orbit tuning again. We fixed some periodicity errors. Still has a second, 0.3, 0.7 seconds. Low enough thrust levels. We're still getting some correction here out of the RCS, even though we're not seeing anything graphically. So I'm not sure what is going on with the orbital period. It's jumping up and down significantly. So our orbital period of 1 day and 1 hour seems to have some inherent uncertainties in it, which are causing us to bop up and down by some fraction of a second without actually doing anything with our control systems. And I mean anything. But on average, this is going to keep us in a good enough orbit. So we have one left to go into our constellation. I'm going to go ahead and launch that. So the only thing I didn't talk about in here, we had this if wait time is long, then we potentially can time warp. If the wait time isn't that long, then we're going to get called back every second or so. If it's very short, if it's less than 2 seconds but positive, we're going to return. We're going to try to nail it right on. And in the end, if we get all the way down to the bottom, this says basically call us every cycle. So this code is being called way too often. I need to rework it at some point and verify that it can be set up so that I only reestablish this DV every 5 seconds or so. So this basically is saying as fast as possible. Anyway, so that's maneuver. Let's get our last satellite going here. So 216 plus 72 is 288. So what else? We have modified plan locally. I think that's covered all of the interesting things about the code. We do have a few to-dos that I've mentioned during the video, which I'm going to work on. Hopefully when we start putting satellites around Minmus, I will have that worked out. So the reason why we had no audio is because I've been working with some new audio mixer stuff, and there's the sound from the game. For what we were doing today, the game sound didn't really add anything to it. I probably could have left it in the background at a low level. So what does our satellite constellation look like now? So here we have our concentric rings around Kerbin at 1 day, 2 days, and 4 days period. And now we've got this set of 5 around Mun. These nice strong connections between the satellites around Mun and the last ring here. And the first time we get a time warp, you'll see a nice display of how these orbits interact with each other. Yeah, I think we'll leave it right there so that we can see it all lit up. And again, this is just the normal sequencing. Our last satellite is still ascending through the atmosphere. Oh, there's time warp. Okay, so it's in space. You could hear and then see RCS triggering off here as it gets into position to circularize. So this particular burn, KSP knows the second half of the burn is going to take longer, but my code took my current engines and did the delta V calculation based on just those. So this burn is going to take longer than I thought it should. So I started at the wrong time. Well, actually, it takes longer. Anyway, so I started at a time different from when I should have started. I end up burning at slightly the wrong time, which is one of the reasons why this initial transfer orbit is consistently needing a correction. Oh, this was the circularization. Very stupid tonight. Yeah, that was circularization. That's fine. It was still a bit confused, but I follow up on the circularization with a error corrector that circularizes. But you see, as we are firing our RCS to get reoriented, our orbit is changing subtly. Part of that is that RCS is changing our velocity along with our angular rate because it's not perfectly balanced. And then part of it is that our ascending node and descending node here are wobbling around because they're not too terribly stable as small. So a small change in the orbit will move those a long way. Okay, so you can see our inner ring is moving faster than the other two. This is why you can't just build one string of satellites going out to Mun, because they wouldn't stay in a line. Now, you notice these long spikes. This is because I have upgraded my my base all the way. So its antennas are actually really good. And in fact, we don't need any of these relays here. We could, in fact, turn on other ground stations around Kerbin. I explicitly turned them off. They're on by default. I've turned them off because if you have the other ground stations, you literally don't need any other satellites in orbit. But I did want to do a constellation of satellites for communication. It's kind of a mission thing. Same thing with Mun. I could make do with a couple of satellites, maybe one satellite that's kind of wandering around out there. We don't need 24-hour, 24/7 coverage. But I wanted to have a constellation just because that's the right thing to do. And there was the sound of a lightning ship. And there we go. We've time warped forward to our correction maneuver. So there it is, without quite so much CurbNet connections. You can see where we're going. And then I turn them back on. You can see what the CurbNet looks like. At this point, I am going to refocus on the moon. I do this to make it look right. Okay, there's the display I like to have, which just shows the links from my vessel to other vessels. So from the point of view of the moon, notice the vessel is kind of creeping up and it'll get swept into my SOI just right there and kind of arc across. And this point over here is, as we arc across, I would leave here and it'll be here by the time. So the time it takes for me to go from here to here, this point on this orbit will slide across the display to the same place. Okay, there's our transition. We have arrived in Moon's SOI. I'm going to go to the local view. There's one camera control I would like to have, which is basically this view. Instead of locked to my vessel or chase or something, a target view. So it's something that I think of as target lock, based on what Falcon 3 did all those years ago, where your view shows your vessel here and it shows your target vessel somewhere visible on the screen, like always above it or something. Padlock view, I think they call it. I mean, imagine you're sitting in a fighter plane and you're maneuvering around the fighter plane, but you always have your head turned so that you've got your target dead center in your eye. This is the view that you would have. If I could set for this view and just have it automatically track, that would be really nice. Haven't figured out how to manipulate the camera from within KOS, though. We apparently have some debris out there. Oh, I have reconfigured KSP to discard my persistent, to not have any persistent debris, because with all the satellites I was putting up, each one of them had a whole bunch of pieces of debris. Cleaning that out took a very long time, and I gave up about a quarter of the way into it after a few hours. I exaggerate slightly. It seemed like it was taking forever to clean up, so I just put the persistent debris slider to 0, and now I don't worry about it. If it's debris, it's going to go away at some point. The alternative would be to very carefully plan all of my missions so that every time I jettisoned something, it was in an orbit that impacted somebody, which would mean for my correction orbits, if I was going to jettison during a correction orbit, I would have to arrange for that to happen while my orbit intersected a body. Okay, we are in the transfer orbit now. You can see us coming down and joining up our orbit. Let me turn on my relays here. Ugh. Hard to see them really. That actually works a little bit better. I can see where they are because they're lighting up my radio links. Okay, so first big burn is our major correction, and that'll be followed by some main engine burns to tweak the orbit a few times, and then it'll give me my final RCS puff, at which point we will be done. So that's 5 satellites in a formation over Mun, and that was about an hour and a half of live streaming. So I'm going to go spend a while debugging and refining this. Oh, we got another burn coming up. Spend a while refining this to eliminate things like these trivial burns. So a burn that's this small doesn't really need to happen. We can skip it. So refine that, refine the entry into the orbit so that we don't assume that we're circular at any point. Try to get code working for proper eccentric orbits and proper inclined orbits, controlling our argument of periapsis and controlling our longitude of the ascending node. If I can get all that going, we can put ourselves literally in arbitrary orbits around Kerbin, Mun, or Minmus. And with that in place, get some stuff in orbit around Mun and Minmus and do some science and open up some things, and we can start thinking about maybe going interplanetary one of these months. And one of the reasons I'm doing this is my intention is to take all of this knowledge, all of these algorithms and all this code, and port it over into Kerbal Space Program 2, where there is a add-on that's similar in idea to KOS. It's called Control System 2. The language implemented by KS2, moving between KOS and KS2, is a lot like moving between Fortran 66 and Rust. KOS had an initial aesthetic where they were trying to look a lot like early Fortran and COBOL, while also making explicit decisions to do things differently from normal coders. So instead of a while loop, you had an until loop. Some of the decisions were merely made to be different. And it made it an interesting thing to learn. It made it an interesting exercise. But at the root of it, it's still a very Fortran-like language. Witness the fact that I've had to roll my own packaging mechanism. Control System 2 uses a .to2 file called 1202 code, and it has some more modern language concepts built in. Like I said, the flavor goes from Fortran on one side to Rust on the other. It's not Rust. He did not embed a Rust compiler into KOS. It might have been interesting. I keep hoping someday somebody will implement Lua for this. Hint, hint. but I'm not a C-sharp expert, so I'm not going to be doing that. So we now have this satellite, 288, in its hold code. And if we switch this to, there we go. This shows CurbNet. There's our 5 satellites in orbit around Mun. There's the whole thing there. I am going to put us up in a time warp so we can watch time crawling forward. So as all the wheels are spinning around, let's focus on Kerbin for a bit. So at times 100 speed, things move very slowly. Let's go up to 1,000. You can see how the connections are making and breaking. You can see how the constellation is maintaining radio communications where we don't have direct communications on the far side of Kerbin. And you'll notice that when the moon sets, all of our links from Mun are now indirect. So getting from Mun back here, if we look up here, we see we only have a 21% signal strength. There's our path. And notice with our 21% signal strength, it's actually giving us a list of all of the relays we're going through. This says we have 2 bars into C03 ring 4 at 336 and 3 bars into ring 2 at 210. Then we hop through the lead element of ring 1 and then through 315 in ring 1, and finally we can get back to KSC. So all those hops together give us a 21% signal strength. If we were relaying science, it would take extra long. But we do have communication. The important thing is we have a connection at all. And for better connections, we will simply need to have better antennas on the ships, which will, well, hopefully it means that we can get rid of having this many things. But to do that, we need to unlock even more science back at the Space Center. I have a bunch of science I could spend, but I'm holding off. I want to do as much as I could do without unlocking any additional science. I think we may have gone a little overboard here, but I like it. Anyways, that's it for this stream. I'll be back when I start working on sending somebody out to Menmis. I think I'm going to need a bigger antenna. Talk to you then.